So we'll continue with CMA 4, which is model analysis. That's both qualitative analysis that Dr. Hafiz started with us, and then we are now moving to the quantitative analysis aspect of the course. And today we'll be looking at sensitivity analysis. Sensitivity analysis. What is sensitivity analysis? It's a statistical technique that is used to understand how changes in the input parameters of a model impacts the outputs. You have a model, you've developed a compartmental model, you've carried out some analysis on it. You've got your parameter values. You want to see the inputs, um, the inputs parameters or the input of those model. How do they affect the model outputs? Model output could be in form of the basic reproduction number. We talked about the basic reproduction number the other time, or it could be in terms of I of t, the prevalence, and so on. So sensitivity analysis aims to identify the model parameters or inputs that have the greatest impact on model output. So we want to see which of these particular parameters is driving the disease dynamics. Say you develop a model for malaria, and then you want to know which of the parameters of this model is driving or is influencing the R naught greatly. This type of analysis helps modelers understand which parameters require more precise estimation and which have little influence on model behavior. So we want to know which one have now. So if you carry out sensitivity analysis and then you get those parameters that are greatly influencing your model output, you know that, oh, if I want to carry out my parameter estimations, these are the parameters I need to be careful about. These are the parameters I need to work more to be much more accurate. And there are basically two types of sensitivity analysis. The first one is the local sensitivity analysis, and then we also have the global sensitivity analysis. So for local sensitivity analysis, you are examining the change in the output values that result from the change in a single input value. So for local, we are looking at just a single input value. We'll see some examples as time goes on. While for global sensitivity analysis, we want to examine the change in the output values that result for changes in all parameter values over the parameter ranges. That is, over the entire parameter space. Is that clear? For local, the basic difference is that for local sensitivity analysis, we are just looking at a baseline value for that parameter. Say transmission rate, beta. We have just a single value. So for local sensitivity analysis, we are looking at how maybe say R naught changes as a result of changes in transmission rate, and just for a single point at a single point. Whereas for global sensitivity analysis, we are looking at a range of values, the parameter space. So for global sensitivity analysis, we'll be needing say range of values for beta. For my recovery rate, I need a range of value. Is that clear? So that it can explore all those parameter values and then pick out plausible values to work with. Is that clear? So let's see local sensitivity analysis. How do we carry out local sensitivity analysis? It evaluates sensitivity at a single point, just like I mentioned earlier, usually the baseline. It involves computing partial derivatives or normalized sensitivity indices. Those of us that have mathematical background, we are familiar with partial derivatives. In fact, even for this school, we've been talking about derivatives, how quantities change with respect to time. For a model with output yt and parameter pi, the local sensitivity index is given as this formula. That's partial derivative of yt with respect to the parameter pi times pi over yt. So remember, yt is the output, the model outcome, and we said it can be your R naught. Why PIs are the what? What are the PIs? The parameters of the of your model. So for local sensitivity analysis, we use partial derivative to compute that. Now, how do we interpret sensitivity index results? If we have positive SI, this is our SI, recall, my XI is given as this. So if I have positive SI, it implies that there is a positive relationship. That is, when the parameter increases, it means that the model output that I'm considering will also what? Increase. If I have a positive, if my XI is a positive, it gives me a positive value. And if it's a negative SI, it means that there's a negative relationship. That is, when the parameter increases, if I increase the parameter, what happens to my output? It will decrease. There's a negative relationship. Then the higher the absolute value of SI, the stronger the relationship. And YT is more sensitive to changes in the parameter value. SI values lie between -1 and 1. Now, values that are closest to -1 or 1 indicate that these parameters are more sensitive to your model output, while values that are close to 0 indicate very little sensitivity. We will see examples to help us drive home this point. So let's look at a simple SIR model. We are familiar with this type of models. So I try to give the model description, the parameters and their description. So we have the ST equals to mu n minus beta SI over n. Look at the incidence function there. What type of incidence function do we have here? Is it mass, action, or standard? Is what? Is it mass? Dr. Abidemi took us through the types of incidence functions. So this is what? This is standard incidence. If it's mass action, we won't have the denominator n there. Is that clear? So this is standard incidence. Then we have the rate at which the susceptible class is changing is given as that. Then the IDT is also given as this. Beta is the transmission rate, and then we have a baseline value, which is 0.0901. Then mu is the death rate, natural death rate. Can we see that? Mu is the natural death rate, and then alpha is the what? Recovery rate, the rate at which people recover after they've completed the infectious period, and then they recover and then they move to the R class. So what is the basic reproduction number for that model? Can we quickly compute it? We can just look at it and just compute. What's the basic reproduction number? We did basic reproduction number during the course of this school. How did we define basic reproduction number? Firstly, who will remind us? Media, where is the microphone? How did we define the basic reproduction number? Okay, this is talking. Basic reproduction number is important, very crucial concept in epidemiology.
The basic reproduction number is the number of secondary infections that occur successively as the disease progresses.
Here, who else wants to help us? The basic reproduction number. Yes, somebody here. The basic reproduction number. How not?
All right, so the basic reproduction number is the average number of secondary infections produced by one infected person in a perfectly susceptible population where there is no immunity or vaccination.
Wow, that's beautiful. The average number of secondary infections generated by what? A single infectious individual during its entire infectious period in a completely susceptible population. Take note of the key words in that definition. The average number of what? Secondary infection that is being produced by a single infectious person That means if we pick an infectious person, if we put an infectious person now into this, say this population is entirely susceptible, what is the potential of that guy? How many people can that fellow infect throughout its entire infectious period? So what is the basic reproduction number for our model? Quickly, who has calculated it for us? By just looking at it, you can, without using, you know, Dr. Epidemiology taught us how to compute basic reproduction number using the next generation method. But then this is a simple model, so we necessarily do not need to go through the NGM to compute this. So who has gotten that for us? Beta over what? Alpha plus mu. Beta over alpha plus mu. How did you get that? Maybe you come and help us. Or can you explain to us how you arrived at that? No network. Does it require, is it a package you are trying to install? So what is it? So how did you arrive at beta over what? Huh? How did you arrive at beta over? You said? At DFE. What's DFE? Disease-free equilibrium, okay? S equals to N. He said at DFE, that means at the initial susceptible population. So the initial population, how do we calculate that? We also did, Dr. Epidemiology took us through calculating disease-free equilibrium, endemic equilibrium. So to do that, we equate that equation to 0. Is it not? Equate the right hand side of the equation. Can we get the slide? Okay, let me see if I can recall that guy. So this, the SDT is what? Mu n minus beta si minus mu s. So equates this guy to 0. And then we also have what? The I dt is what? Okay, over n beta si over n minus what? Alpha plus mu I equals to 0. And then dr dt equals to what? Alpha I minus what? Mu r. So to obtain our disease-free equilibrium, that we want to find when there's no disease in the population, we equate the right-hand side of this equation to 0. And then we also do what? We set the I. We set I to what? 0. Set I to 0. So if we set I to 0, this guy blows out. This guy also what? So this places everywhere blows out. So I equals to 0 here. We don't have anything here. We also have I here. So this guy becomes what? 0. So I is also what? 0 here, is it not? So if I is 0 here, what is left here? So we have mu r equals to 0. So it means that what? Okay, minus mu r equals to 0. So that means what? It means r equals to 0. So you can divide and then you see that r equals to 0. So if r equals, so I is 0, r is 0. What about our s? So s here we have mu n left minus what? Mu s equals to what? 0. So we have what? Mu s equals to what? Mu n. And then if we can divide through by what? Mu. So we have that what? S equals to what? That means S star equals to N star. So at initial susceptible, our susceptible population equals to the entire population at time t equals to 0. And so remember that our incidence, what's our incidence now? The incidence rate is what? What's my incidence rate? The incidence rate is what? No. What's the incidence rate from the model or the incidence function? Beta what? Beta Si over what? Over n. Over n. So what's for one infectious individual? What do we have? For one infectious individual, that's I equals to 1. So we're going to have what? Beta S over what? N. And then at initial susceptible population, what do we have? Remember, at initial susceptible population, we have that what? Beta or beta S star over n is what? You can use at initial susceptible population, we have n star. Remember, we have that what? S star equals to what? N star. So we can substitute that, and then this guy is what? We have beta left. Is that clear? At initial susceptible population, S star equals to N star. So in place of S star now, we replace it with N star, and then we have beta there. So we have beta now. That's the transmission, the average number of transmission that one infectious person will generate, times the infectious period. What is the infectious period? Remember our definition of basic reproduction number. The average number of secondary infection that one infectious person will generate over its entire what? Infectious period in a completely susceptible population. So what is the infectious period? Can we go back to the slide, media? Let's see. What is the infectious period for this model? What's the infectious period? What is the rate at which people are leaving the infectious class? This infectious class, the the T, beta Si over n minus alpha plus mu I. So what's the rate at which people are leaving the infectious class? The rate at which they are leaving the infectious class is alpha plus mu. Alpha via what? Alpha is what? They are leaving via what? For alpha, via recovery. When people recover, they leave the infectious class. Is that clear? How else can they leave the infectious class? By natural death. When they die, they also leave the infectious class. So the rate at which individuals or infected individuals leave the infectious class is alpha over mu. And so the duration, the period that the infectious period will now be what? The inverse, 1 over alpha plus mu. So if the rate at which people, or maybe the rate of progression or the rate of recovery, if people are recovering at a particular rate, alpha, that means the infectious period will be what? 1 over what? The rate at which they are leaving that place. Is that clear? Do we get that? Let me come again. The rate at which a particular how do I put that now? Now the rate at which they are leaving a particular compartment, a particular class, the rate at which people are leaving a particular class. Now, if you want to calculate the period they spend in that class, you can get it by doing what? 1 over the inverse of the rate at which they are staying there. So if we are looking at the rate at which people are recovering, how do people recover? Remember, recovery is a function of the infectious period. How long do they stay in the infectious class? So to get the recovery rate, you have what? 1 over this. So if the rate at which they are leaving the infectious class is this, then the infectious period, the time they spent in that class, is given by 1 over this rate, alpha plus mu. So, and that's how our friend got this as its reproduction number. This is the value of our basic reproduction number. They compute it. You have beta over alpha plus mu. So the basic reproduction number R naught there is beta over alpha plus mu. And so we can use that as our model output. And then we now carry out sensitivity analysis to determine which of the parameters of these models, is it the beta, the mu, or the alpha, which of them have the strongest influence on the R naught? Which of these parameters are driving the basic reproduction number? So let's see how to go about that. So let's look at the first one for beta, the sensitivity index for beta. How do we calculate that? We got that formula earlier. Partial R naught over what? Partial B. Now, partial derivatives, you can think of, just did this. We are familiar with constant classes and heterogeneous class. So let's see how to. What's this? Yes, what? So we are looking at the rate at which what? Susceptible population changes with what? With respect to time. One single variable. This is total derivative. This susceptible class is changing with respect to time. But then we have partial derivatives also. The partial S with respect to, let's say, partial whatever time or with respect to t. That means this guy is a function of several variables. You can think of partial derivatives like baking a cake. If you are baking a cake, and then the taste of the cake is a function of several variables, is it not? It's a function of what? Can we mention of those ingredients? It's a function of sugar. It's also a function of what? It's a function of water. Okay, so let's just pick 3. It's a function of sugar, flour, fire care. Okay, let's say eggs. All right, so let's just use this 3 for instance. The taste of the cake is our function. We now want to see how does it depend on all these guys. Now, if I increase my sugar level, what happens to the taste of the cake? The taste changes. So now, if I want to see how does the taste change with respect to sugar, then I have other variables there. So what I will do is I will keep these other ones constant. I will keep flour level constant. I will keep my egg, every other variable, every other ingredient, I keep them constant, and then I keep what? Changing my what? Sugar level, and see how it affects the taste of the what? Of the cake. So similar concept is that's how partial derivatives work. We are looking at a function that depends on several variables, not one variable, several, and then you want to see how does that dependent variable change with respect to maybe one of those independent variables, and then you keep other words, other variables, other independent variables constant. So that's what partial derivative is all about. So can we go back to the slide? So we have partial derivative of R naught with respect to what? With respect to beta. So we have partial derivative R naught with respect to beta times what? Beta over R naught. So we have my R naught is what? Beta over what? Alpha plus mu. So how do we differentiate this guy partially? What will it give us? Huh? How do we do it? We keep what? So we are differentiating with respect to beta. So you keep other parameters, other independent variables, constants. Maybe would for those without math background, people would find a time to explain how this how derivatives are being done. Because I don't know if I start doing that, it might take a lot of our time now. So if we differentiate this guy partially with respect to beta, what do we have? We have what? 1 over what? Alpha plus mu. If we differentiate partially, we are keeping alpha and we are keeping this guy constant. I mean, we are keeping these guys constant and we are varying beta. Is it clear? So we keep these guys constant, and then when you differentiate, you are differentiating a variable with respect to itself. What will it give us? It will give us 1. So if we differentiate beta with respect to beta, it gives us 1. This guy is constant. We can bring it out since partial derivative is a linear function. So we have that. So we have 1 over alpha plus mu times beta over our r naught. And so remember that we have our values, our baseline values earlier. The baseline value, we go back to the slide. We have some, the baseline value for beta is 0.0901. For mu, it's given as that, and then for alpha, similarly. So if we substitute these values into the result we got, what do we have our sensitivity index? Our sensitivity index is what? 1. Now, how do you interpret that? Firstly, you observe that the sensitivity index is positive. Is it true? It's positive, plus 1. So what does positive mean? What does it mean when our SI is positive? We mentioned it earlier. As that parameter increases, the model output, in this case, our R naught, also what? Increases. There's a positive correlation there. So it implies that an increase in beta, the transmission rate, will lead to what? A corresponding increase in R naught. Does it make sense biologically? Does it make sense biologically? Think about it. That as the transmission rate is increasing, the basic reproduction number, the average number of secondary infection that is being generated also what? Increases. So biologically it makes sense. Is that right? So we see that since it is positive, an increase in beta will lead to a corresponding increase in R naught. Also, the sensitivity index with respect to beta is 1, which is the highest value that we can obtain. Remember, we said that sensitivity index is usually between what? -1 and 1. Now, the closer it is to 1 or to -1, the stronger it is, the stronger the correlation between them. So this implies that R naught is extremely sensitive to any changes in beta because the sensitivity index is 1, and that's the highest. So our R naught is very sensitive. Any little change you apply to your transmission rates in your model will affect your basic reproduction number. And so if you want to carry out, say, parameter estimation, you know that you have to be very careful with the way you handle your transmission rate. That beta is very sensitive. If somebody is very sensitive, what do you do to that person? Somebody is very sensitive person. How do you deal with the person? You are very careful with the way you handle that person. You don't misbehave around that person. The same thing with this guy called beta. He's very sensitive. I mean, the R naught is very sensitive to beta. So you want to be careful with the way you deal with beta. So let's see for the other 2 parameters. Sensitivity index for alpha. Alpha is what? Remember, is what? Alpha is our recovery rate. So we use the same formula. And then here we're having a different partial derivative for alpha. The those mathematically inclined will understand how that happens. Abi? When we differentiated that guy with respect to alpha, what did they give us? It gave us what? Minus what? So we differentiate partially now. We are differentiating our R naught partially with respect to alpha, and we got what? Minus what? Beta over alpha plus mu squared. What did we use here? We use what? We use product rule. Product. So if those sorry, where did I hear product rule from? It's not chain rule. Oh. Quotient rule. We use quotient rule here because it's a quotient, and then we are beta is we take beta as constant, and then mu is also constant. So you apply quotient rule, not product rule. You apply quotient rule. So those that maybe after the class you can meet one or two persons to show you how that how we arrive at minus beta over alpha plus mu squared. So that's the result of the partial derivative times alpha over R naught. Remember, the value of alpha is what? The baseline value for alpha is what? 0.045. And then we got that as our sensitivity index. Minus what? Minus 0. What does the negative sign mean? There's a negative relation. No, the negative sign. What does the negative sign mean? It means that what? There's a negative relationship. So if we what? If there's an increase in alpha, what will happen to R? There will be a decrease in my R naught. And then it also makes sense biologically. Can you think of it? Think of it and see that it makes sense biologically. Is that true? Biologically, this makes sense since alpha is the recovery rate. So an increase in alpha, if there's an increase in alpha, the increase in the recovery rate, it means that what? People are recovering faster than the period they stay being infectious. And so they have a shorter time being infectious. So what happens to our R naught? Our R naught will reduce because remember that R naught is also a function of infectious period. Remember the definition for R naught. The average number of secondary infections that is being generated by what? One infectious over its entire infectious period. So it means if the person spends longer time being infectious, say one person, the infectious period of a particular person maybe is 20 days. That means for 20 days that guy will just be infecting people. Another person has an infectious period of say 2 days. After that infectious period, this person recovers. So you see that if infectious period is shorter, it means that what we have a person had a short time to infect, and so that makes sense for our recovery rate being negative. There is a negative relationship there. Then since 0.99 is very close to 1, what happens? It shows that R naught is very sensitive to changes in alpha, just like the first one that is 1. This one is also very close to 1, 0.99. Yes, it's negative, so it's a negative. So that means if I increase what? If I increase what? My alpha, what will happen? R naught will go down. So if I want to target, maybe I want to look at a control measure for the disease. You want to advise policymakers from the model, from the sensitivity analysis. You can tell policymakers, okay, if we do what to the infectious period, to the recovery rate, if there's a way you can target the disease such that, or we can treat the disease so that people recover faster, what will happen to the recovery rate? People will recover at what? quicker, and then the R naught will decrease. So it shows that an increase in recovery rate in alpha, that means faster recovery. When there's a faster, when people recover very fast, it's when the shorter time being infectious, and then they cannot they cannot they cannot spread the disease just anyhow. And then you can now suggest ways. What are the ways you can use to make recovery faster? You can say, okay, let's start treatment. Let there be rollout of, if it's for malaria, let there be rollout of ACT. Let there be treatment for malaria so that people can recover faster. And then since 0.999 is very close to 1, it shows that what? R naught is very sensitive to changes in alpha. So R naught is also very sensitive. It's sensitive to the recovery rates. So let's look at this last parameter. What's the last parameter we have there? Mu. Look at mu. Similarly, we do the partial derivatives, and then we obtain that, and then we got for our sensitivity index minus 0.0011, negative again. So what does that mean? It means that one increase in mu will lead to what? So biologically, does that also make sense? Who can explain to us how it makes sense biologically? Okay, somebody wants to explain how it makes sense biologically that an increase in the death rate will lead to a decrease in our R naught. Okay, yes.
Okay, if the infectious person dies naturally, then there cannot be transmission of the infection from him to another person. So that is, once he's removed from there, then the reproduction number that is supposed to be the average number of secondary infection will actually not be there for that person that is dead.
Okay, so you see that if people die, they are living infections, they are die fast, you cannot see what's reduced. So what do you suggest? What do you advise policymakers? What do you advise policymakers? You do what? Kill people. So that kill infection, so that they have shorter time to live. They cannot transmit the disease. So, but you will see that for this particular parameter, it's not very sensitive. The value is very close to 0. Can you see that? Can you help us bring the slide? It's very close to 0, 0.001. So a sensitive index of minus 0.001 is very close to 0. Because R naught is not sensitive to changes in mu. It's not sensitive to that change. So a small change the parameter mu with a small change. It will not cause any significant change in your model results, unlike the first two that we had, where we had 0.999 and then 1. Is that clear? So let's see the result interpretation. So the sensitivity index, if the what? The mu value is close to, so if it's close to 1, yeah, it means that it's that means our R naught is very sensitive. For instance, I did sensitivity index for a malaria model sometimes ago, and just like our mu here, the mu m for mosquitoes now, not for humans. So it means that we need to put in more control measures that target killing those mosquitoes. But if it goes on the side of human, you can't advise policymakers to kill people. I remember those days in my secondary school, I saw something on the wall. I don't know who wrote it. On the wall, it said to reduce the population of Nigeria, kill a friend. I don't know who wrote it. One of those boys then, they write so many things on the wall. they write a lot of things and then you put to reduce, you say kid in friend. Now that is not ethical. Even though your result might show that okay, natural death rates, the R naught is sensitive, but then it is not ethical to give policymakers such advice. So what is our results interpretation? So the three sensitivity indices, one minus 0.99 and then minus 0.001. This slide, please. We try to put it in a plot to see. So you see that beta, R naught is very sensitive to beta. Beta, the sensitivity index is 1. And then for alpha 2. But for mu, very what? Very small. It has no significant impact on our R naught. So beta and alpha have a great influence on R naught. A small change in beta and alpha can result in a large change in the R naught. So these parameters should be estimated as accurately as possible. And also, control interventions should be targeted at these parameters. So what can we suggest? What control intervention can we suggest that will target the first parameter? Somebody should help us. We want to advise policymakers. What control intervention can you advise to target beta so that who is talking? Somebody is saying something. Can you get the mic? We want to rule out control interventions to target beta, the transmission rates.
We can look at, like in case of COVID-19, social distancing, because social distancing reduces the interaction rates. We can also look at enlightenment and inform people. When you enlighten people on the dynamics of the disease, they will take precautionary measures.
Remember the function of beta is the function of what? Beta equals to what? P probability, C times what? P. The contact times what? Probability of what? Infection giving a contact. So you want to advise policymakers, you can tell them, okay, to control this guy, to reduce the transmission rates, because remember the relationship, the more there's an increase in beta, there will be a what? Increase in what? In R dots. So what do? We want to what? Bring down the transmission rates. So how do we bring down this guy? We mentioned COVID-19. For COVID-19 to reduce the transmission rates, you can use social distancing. You can advise what? Face masks. Is it not? You can advise face masks, hand washing. So those are control interventions, control measures that can target beta. Is that clear? What about the second guy, alpha? How do we target alpha? What control intervention can be targeted at alpha? First, treatment, because we want to make the recovery rates faster. So we can advise prompt treatment and all that. We boost the immune system. Thank you very much. It will help. So probably there will be, what can we use to boost the immune system? They eat good food, nutritious food, balanced diet. So those can aid the recovery faster, and then we can advise those. So that's that for local sensitivity analysis. Let's see if we still have time for global sensitivity analysis. So for global sensitivity analysis, it explores the full input space and assesses sensitivity over the entire distribution of input variables. GSA involves sampling methods such as the Monte Carlo sampling, the Latin hypercube, and then uniform sampling to explore parameter space. So for global sensitivity analysis, unlike the first one, where we just pick a baseline value. Remember, just pick baseline value for beta, which got a baseline value. For alpha, just one value. For mu. So for global sensitivity analysis, we are looking at a range of values. Plausible values for maybe beta. Plausible values call them say x1, x2, or say for beta we can have 0. If my x1 can be 0.02, my x2 can be 0.111, and then we look at this space of parameters, so it explores the entire range of parameters and does sampling, does maybe random sampling, and generate or draws out samples from that range of parameters. So method of DSA include the PRCC, Subo, the Morris, etc. I'm going to there is a paper in the publication that really talks about global scientific analysis. So after this class, I'll try and share it so that those interested can go through it. And one of the most popular sampling method in scientific analysis is the Latin hypercube sampling. It's being combined with PRCC, partial rank correlation coefficient. So we perform global scientific analysis using the PRCC, usually combined with the Latin hypercube sampling. So let's describe this procedure using an SCIR model. An SCIR model, the SDT. Can we go to the slide? The SDT is lambda minus, lambda is what? Capital lambda is what? The recruitment rate, beta SI minus mu S, and then we have introduced the exposed class, the pre-infectious class. Beta is the transmission rate with its own range. We also have mu, it also have its own parameter range, then sigma, V, and then gamma. The R naught is calculated first. So as an exercise, how did we obtain this? That will be our exercise maybe during when should we submit the assignment? How did we arrive at it? So you can try using the next generation method that Dr. Afis taught us. You can also do it using just you can visually inspect it and then see that that is actually the basic reproduction number. Look at the infection, time spent in doing in the infected classes and all that. So we can look at how we obtain the basic reproduction number. So our R naught here is our model output, and then we can also we now want to see how sensitive R naught to each of the parameters. Now it is not only on R naught to do your, you can also do prevalence on the epidemic peaks and all that. What's our prevalence here? What's my prevalence from this model? My prevalence is what? What is prevalence? Beta SI. Don't leave this place. Don't go and say it outside. Though. What is my prevalence from the model? Beta SI is the what? Is the incidence. Incidence is what? Number of what? New cases. Number of new cases. So what's the prevalence here? What is the definition? How do we define prevalence? Prevalence is what? Prevalence is total number of what? Cases. That means both old and what? New cases. Old and new cases. So what variable represent our prevalence there? The I is our prevalence. Our incidence is beta SI, the new cases coming in, and then I is our prevalence. So you can also do sensitivity analysis using I as your model output, the outputs you want to consider, and how being sensitive to other parameters. So the Latin hypercube sampling, plausible ranges of parameters are defined for LHS sampling. The LHS is a stratified Monte Carlo sampling method that divides the parameters range into n equal intervals and randomly draws one sample from each interval such that the entire range of each parameter is covered. So what the Latin hypercube does is that you have your parameter range. So So if this is my parameter range, media, so I have the entire parameter space, and then it say we want to divide it into 100 intervals. So I can have one in the first interval, another interval 2, another interval 3, and then it divides it into 100 intervals. Now in each interval it draws a particular parameter randomly. It draws from each interval. So I'm going to have how many parameters in all? 100 parameter, because we have 100 intervals. So in each interval it draws a parameter randomly, and it's one of the most popular, one of the most accurate sampling method. So for instance, if you want to sample 100 points, the range of each parameter, if the transmission rate, you can pick transmission rate, is divided into 100 intervals, and one value is randomly chosen from each interval. So I tried to just do some, even though I couldn't put that. So remember our R naught, if these are the parameters in our R naught: beta, sigma, gamma, mu, and d. So these are the values, the parameter values that our LHS generated after it has divided it into 100 intervals. So due for the first interval 0.25, 0.7, like that, 100 of them. The same thing for sigma, 100 parameters, like that. And then we can now compute our R naught. We can have a value for our R naught, is it not? Remember the formula. What's the expression for our R naught? Our R naught is what? Sigma, beta, lambda, beta, sigma. So you put all those values, and then you can estimate your R naught with these values. So we have R naught values also similar manner. Now we see how the PRCC. So the PRCC is a statistical method that is used to determine the temperature of an output variable to an input parameter while controlling for the effects of other parameters. It measures the linear correlation between the residuals of the ranked input and output variables after removing the linear effect of other parameters, and it's usually between -1 and +1, with an absolute value of PRCC close to 1, indicating that the parameter has a strong impact. If it is close to -1 or 1, it means that it has a strong impact on the model. So I'm just trying to see, we'll look at even though we will not have time to look at code, we'll send it to you, but I'll try and run through the code to see how it works, and then we can send the code so that we go and then run it. Because we also require installing some packages that we don't have all the time. So, but these are the background process that is going on in your code. The code will be running. This is the background, the underground things, underground processes that are ongoing. So you now rank transform. We carry out rank transformation. SJ, the date input parameter, is rank transformed, while the output state variable is also rank transformed. So what we do is, let's go back to this guy. So we rank transform all these guys, also rank transform this, everything up to R naught. So what we put ranks to them. The smallest, we assign the smallest value. What's the smallest value here? For beta, 0.25, we rank that 1. The next one is what? 0.45, we rank it 2, like that. You rank each of the parameters. You also rank your R naught. That's what that step is saying, rank transformation. XJ, the jth input parameter. So in this case, my XJ can be what? My XJ can be what? My XJ can be 2. Is it 2? What is XJ? XJ, the jth input parameter. So what is my XJ? Somebody to give me my xj, one xj. No. Xj, the jth input parameter. So what are my, how many xj's do I have in my model? Therefore, how many input parameters do I have? 100k. How many input parameters do we have? We have 5 input parameters: beta, sigma, lambda, mu, t, and then r naught, which is the output, the model output. So xj, I can have x1. X1 is what? Beta. X2 is what? Sigma. I can call S3 as gamma, like that. So xj, the jth input parameter. If I have x2, that will be the second what? So what is my second input parameter? Sigma. The second input parameter, sigma. Is that clear? So xj, the jth input parameter, is rank transform. The one in focus now, let's say beta now, x1, the first input parameter, you rank transform it. Also y, the output state variable. What's my output state variable here now? R naught is the output. It's also rank transformed. And then you now replace the original values of those parameters with their what? With their ranks. You replace each of them with their ranks. You replace this guy with its rank, this guy with its rank, and then R naught with its rank. Then we also carry out linear regression models where we have xj cap here, given as that. Now xj cap and yj cap are the predicted values from linear regression models where the effect. So what that helps us to do, we regress, let's say x1 on the remaining input parameters. If we are considering s2, we regress s2 on the, so it helps to remove the linear effects of the other parameters from the, you want, because you now want to look at, want to see the correlation between, let's say, beta and R naught. So I do a linear regression model to help me remove the effect of those other parameters, because I want only what? Beta and R naught. So it removes the effect of those other parameters. And then we now calculate the residual. The residuals, xj minus sj, that's sj cap, which is the predicted values that we got from our linear regression, and also do the same for your output model. Those two, you determine that. Then you now compute your PRCC, the partial rank correlation coefficient. It's computed as the Pearson correlation coefficient between the two residuals. The residuals xj, which are the transformed, you rank transformed, and then you have your predicted values. You subtract, you get the residuals, and do the same for the output model. And then you now compute the correlation coefficient using this formula, the covariance of xy over what? Standard deviation of x multiplied by the for y. And so that's how the stuff is done. But then most times global sensitivity analysis are not, because of the complexity in computation, they are usually done. We use software to compute them. Use MATLAB, R, and all that. So let's quickly see how this is being done in R. Okay, so this is the reference I mentioned. It's a very good work on sensitivity analysis. Sensitivity analysis of infectious disease models, advances and their applications. It's a very good book. We will send it to the group so that those that are interested can go through it to see other methods of sensitivity analysis. So let's see the code. Let's see how to do this in R. Media. So we install packages, sensitivity analysis. I've commented them out because I don't need to install them again. And then you load the packages. So we generate sample data, maybe 100, number of simulation, number of the parameters you want for your display. Here we are not using the Latin hypercube to sample. Just pick them. We looked at a range of values. These are the parameters under consideration: beta, gamma, sigma, lambda, and d. These are the parameters we want to check. So we did a 30% deviation from the baseline value. Say for instance for beta now, the baseline value BV, hash BV, you can see BV on line 11, and we see BV of 0.6 on line 11. So that BV is the baseline value for our transmission rate, 0.6. So we now did a 30% deviation from the baseline value, 30% deviation on the left and then on the right. So we have a minimum value of 0.42 and a maximum value of what? 0.78. Where will 0.6 fall in there? Where can we find 0.6 there? It will be at the middle, is it not? 0.6 will be at the mid value there, where we've done a 30% deviation from baseline. So the same thing for the other parameters. If, for instance, for gamma, the baseline value is 1/4 for sigma and all that. But then this line 19, we put all the parameters we want to look at, concatenate them, we put them in vector form. Then you can let's see the first 6 values using head. So we see the first 6 values. How many simulations did we put initially? 100, but the head will give us the first 6 values. So for beta, we can see that we have these are the range of values of parameters for beta: 0.566, 0.6, up to 100. But the more the number of simulations, the more accurate your results. Although the longer time it will take for the listing for the codes to run. So it's advisable maybe use 1,000 simulations, 2,000. But then the more accurate, but then the longer time it takes. So I just use 100 just for simplicity. So we perform the sensitivity analysis. Our Y is given as this, where this is my R0. That's the value of my R0. Expression R0, lambda times beta times sigma over that. Then we also did the line 24, the PCC for that. Then we can print it and we plot using GD plots. In subsequent R classes, we'll be having lectures on visualizations, how to visualize using GD plot. So we'll be taking through GD plot, and then we can print this guy out, and then it gave us this result here. So you see beta. Beta is what? Is beta sensitive or not? Is it a sensitive parameter or not? How do we judge? It's very close to 1. Remember we said values that are close to 1 or minus 1 means they are very sensitive parameter. So beta is a very sensitive parameter. It's very close to 1, maybe 0.8 or something. And then gamma also. Firstly, it's a positive. For beta, it's a positive correlation, is it not? So if we increase beta, if there's an increase in our transmission rate, there will also be what? a corresponding increase in R naught. Then for gamma, is it a sensitive parameter or not? Strong correlation. There's a strong, but it's a negative one. So it's an inverse relationship. If we increase gamma, what happens to R naught? What will decrease? So it's an inverse correlation. But it's a very strong one. It's close to 1, 2. Sigma is what? Not strong, not so strong. Not so it will not, so sigma will not be very much concerned about sigma because it will not really impact our model. And then we have mu that is also it has a strong negative correlation. Then capital lambda also positive. And D, what is D in our model? D is the disease-induced death rate. D is the disease-induced death rate, but it doesn't really have impact on the model. See that the sensitivity index is very close to 0. So this is how you can interpret some of your sensitivity analysis results. I've shoot past my time. I want to stop at this point. Thank you for listening.